Hi there, this is a quick update on the DPS control program I released end of May. If you recall, at that time I demonstrated one variant of the call instruction in taking an image from a webcam, but the other one taking measurement by some other instrument and inserting the result into the DPS recording was just a dummy script that always reported the same 123.4 value. My only multimeter that I can access remotely to get measurements is the venerable Solartron 7150 Plus using GPIB or the IEEE 488 interface, for which I built an Arduino-based GPIB to USB converter some time ago. I had not used that interface for a while, and when I tried it with the DPS control program, it did not work anymore. The fault turned out to be memory corruption in the Arduino when GPIB was connected and active, but the USB interface was disconnected. I just published a short video about solving this by enabling brownout detection on the ATmega 328PB controller. So with that problem fixed, I looked at the GPIB software I had published for this interface on my GitHub page, which was a GPIB logger to create continuous recording on my PC of the multimeter measurements. For use with a call instruction in a DPS control program, I needed a new program that would just fetch a single value and then terminate. Essentially, the program you see here is very simple. It checks its command line arguments and then opens the serial port. It sends a message to the multimeter asking for the measurement data and then reads the response, prints it out and then terminates. Okay, there's a little bit more to it, but in part this is to make the program usable for other devices which may need different read commands and so on. There are two slight complications that I want to highlight here. First, the Arduino Nano hardware causes a reset every time a serial connection is established. This activates the bootloader, which tries to establish a connection to the Arduino IDE, and in that process could swallow the first couple of bytes from the serial port sent immediately after connecting. The bootloader will eventually realize that it's not wanted and pass control to the usual setup and loop functions in the loaded sketch. So, complication number one is that you need to wait after establishing a connection. That's what the sleep instruction of 2 seconds is for. The second is that going through the setup will cause the sketch to print a welcome message, which we need to discard. I considered removing the welcome, but it has served me well when chasing the memory corruption problem, and it's easy enough to discard since I tag all messages not coming from the GPIB device itself with a leading exclamation mark. The code itself is available on my GitHub page and it works for Linux and Windows, but of course you need to specify the correct port. Speaking of which, there's one additional complication in my setup. It turns out that both my clone Arduino Nano in the GPIB interface and the DPS use exactly the same USB serial interface chip, which reports itself as Quihang Electronics HL340 USB serial adapter. This makes it hard to find which port is connected to which device. Here you see the Windows Device Manager telling us that DPS control and GPIB are using COM ports 6 and 9, but you can't tell which is which. Linux LSUSB has the same problem, but I've started to plug one of the two USB cables into a USB 3 port, and this enables DMESC to report a difference. In this case, DPS control is using USB 3 and the name TTY USB 0, while the GPIB interface is on a USB 2 port and using TTY USB 1. Since my old Windows laptop has no USB 3 ports, I can't tell you if you could use a similar trick to tell them apart. If not, then the only way to find out is trial and error. With the port identification resolved one way or the other, here's a sample run of the program. As you can see, by default, the Solartron 7150 Plus reports the measured value and the unit, here volts DC. The Solartron user manual states that the command N1 changes that to numerical output only. I could have coded that command into the GPIB control program, but that would make it specific to the Solartron, and it's really no big deal to send an N1 manually once after powering up the Solartron. Let's do that now. Sending the N1 command. And now the response is, as expected, just the measured value. With that working, it's time for a new measure script that doesn't just print 123.4. As you can see, it just calls the new GPIB control program to fetch one measurement value and print it. This is the Linux version, but the Windows version would look exactly the same except for using COM6 or whatever port and a different path to the program. What better object to test for the first run than the DPS5005 itself? Basically, a program that increments the voltage on the DPS5005 and at each step measures the output with the 7150 Plus multimeter. That way we get a good idea how accurate the voltage reading of the DPS5005 really is. Here's the program I'm going to use for that. We set over voltage, over current and over power values to not get into our way, and recording to a new value of 4, which I'll explain in a moment. Then we do the usual steps to increment the voltage in 0.5 volt steps all the way to 50 volts, and then turn the power off and set the voltage back to 0. There's a slight change in the syntax of the call instruction. The last parameter is now a comment that gets inserted into the recording file. So in this case, volts at DPS5005. If you had several calls to different instruments measuring different things, the comment part would help you when analyzing the recording later. The program takes many minutes to do the full 100 tests, mainly because I give the voltage time to stabilize and also because of the minimum 2 seconds needed for the Arduino Nano to do its reset at every call of GPIB control. All this is fully automated and very boring. I certainly did not hang around while it was executing, and to spare you, I'm showing only the beginning and the end. Before looking at the results of the voltage test, let's do the second part of verifying the DPS5005, namely to check its current readings. The slight complication is that the Solartron can only measure up to 2 amps, clearly not enough for the 5 amps maximum of the DPS5005. Therefore I use an external high precision shunt resistor of 0.01 ohm, and the Solartron measures the voltage drop across that instead. Using Ohm's law, you can easily calculate that at 5 amps current the voltage across the shunt will be 0.05 volts or 50 millivolts. So all we have to do is to multiply the value measured by the Solartron by 100 to get the currents in amp. This is the program I'm going to use for that. It's basically a mirror image of the one for volts. The only thing to note is that you have to set an output voltage to let current flow, of course. Here I set it to 1 volts. With a shunt of 0.01 ohm at the output, the voltage will of course never reach 1 volt. Instead, the DPS5005 will go immediately in constant current mode and reduce the output voltage to produce the demanded current value. Note that I add a comment to the call instruction as a reminder that the value of this measurement needs to be multiplied by 100 to get amps. Again, the program takes many minutes to complete the 100 test steps. It's a bit hard to see, but the shunt resistor box is right above the DPS5005 display. Let's have a quick look at the recording files produced by these runs. Voltage first. Because the recordings are in CSV format, They open in any spreadsheet program like Excel or in this case LibreOffice Calc. U set, I set and so on all the way to CVCC are values measured by the DPS5005, and here on the right are the results from the calls to the 7150 plus multimeter, followed by the comments. To get an idea of the accuracy of the DPS5005 volts readout, I added this column here, calculating the error in percent between the multimeter readings in column K and the DPS5005 readings in column D. To get a better view, I'm going to plot this column D versus column M. Oops, D, M. As you can see, for almost the whole range of 50 volts, the error stays around 0.2% or less, except at a very low range the error is slightly higher, but still only 0.6% maximum, which is very good. Doing the same for the current recordings. Because the 7150 Plus was actually measuring the voltage drop across a 10 milliohm shunt, the comments add a note that this value here is equivalent to 10 milliamps or 1/100th of an amp. So to get amps and to be able to compare it with the DPS5005, we need to multiply column K with 100. I added the same error calculation as before in column M, taking into account the scaling factor of 100 for K. Again, I've plotted this column E, the output current versus the percent error. You may think, wow, this is bad at low currents. But this is actually not true. In fact, the reason why the error seems to go exponentially up is a result of the calculation method and not because the DPS5005 is increasingly inaccurate. I explained this already in one of my other videos where we have encountered the same issue. In the calculation, the same error gains more and more weight the lower the measured values get, and this causes the exponential rise. So the overall accuracy of the DPS5005 current readings is around 0.5%, still quite a reasonable value. I already mentioned two small changes for the DPS control program based on longer practical experience with it. The first is the record instruction. I added a new value of 4, which records only when a call is executed. This is a great time saver for tests like the one I've just demonstrated, where you want a direct comparison with DPS values and call results only. It saves you to delete all the lines in the recording where only the DPS value change, for example while voltage or current stabilizes. You have seen this recording mode in action when I opened the results of the voltage and amp test. The only rows in it were the 100 test steps, even though the program ran for many minutes. The second change is in the call instruction. The third parameter, if specified, is now treated as a comment to be added to the recording. The real benefit of this will come in test runs using multiple instruments measuring different things, but for now I use it as a reminder if scaling needs to be applied, like the ×100 for current measurements. As the last thing in this video, I want to briefly show a combination of measurements from an external multimeter and taking pictures from a webcam at the same time. It's basically the same setup for measuring amps, but now I included a bunch of multimeters that I have accumulated over time into the current loop to the DPS5005. They're all in series, so should read the same current, and we can compare that with the reading of the DPS5005 or the Solartron 7150 Plus. I choose current over voltage for this test because Since building the DPS5005, I never had a convenient way of creating up to 5 amps of DC current. The amps test program needs a few changes. First of all, I added a second call to get a webcam image. This uses FFmpeg as discussed in my previous video. The R and the N parameter mean that the file name of each image will be the same as the recording file name followed by the sequential call number. I needed to change the output voltage and the overvoltage protection because the large number of multimeters means there's a bigger overall voltage drop. 5 volts isn't overkill though. It turned out that 1.5 volts would have been sufficient. Lastly, I changed the step to 0.1 amp to reduce the number of steps to 50 for a reason that will soon be apparent. After the run, which I did not capture, the folder contains all these images. Note that the call number in the image is going up by 2 because the measurement call also increases the counter. Still, it's easy enough to associate both. Call number 1 is the first Solartron data of 0.1 amp and number 2 the matching image. 3 is the next measurement of 0.2 amps and 4 the associated image, and so on. So let's have a quick step through the images. So yes, to make calculations with that data you need to manually record the values shown on each image, but some trends can be seen right away. The 2 yellow cheap Chinese sinometers bought long ago from a bargain bin in Maplins are pretty much in line with the big no-name meter on the right, which I got years ago from a DIY shop. If 3 meters are consistently agreeing with each other within reasonable limits, this probably means they are close to showing the correct value. Compared to these, the UNI-T clamp meter at the bottom is disappointingly lagging behind, while the most left MA S830 is consistently slightly high. The only way to get better data is to enter the values shown in each image into a spreadsheet together with the associated Solartron measurements converted to amps. It is easier than starting and stopping a continuous video, but it's still tedious work. This is the reason why I limited the run to 50 steps. Can this be automated? I downloaded Google's finest open source optical character recognition or OCR software called Tesseract, compiled and downloaded a 1.5 gigabyte database for it. When run in default mode, on one of the pictures it doesn't produce much sensible output, as you can see. The only thing reliably recognized is the text at the bottom of the UNI-T. Or is it this one? This one. I found the best result was using the same picture enlarged by 400 times and running Tesseract with a page segmentation mode of 11. Let me see that one. This means find as much text as possible in no particular order. It produces a lot more legible output, but still only from the text printed on the meters, like backlight and true RMS, and in general all these legends around the range switches but nothing from the display itself. I did a bit of internet research on this, and it turns out that OCR in general doesn't recognize 7 segment numbers because of the gap between the individual segments. The only solution is to write your own specialized OCR software. It's doable, but way too much work for the task at hand. So back to the old way of looking at each image and typing the displayed values into a spreadsheet. Well, here's the data. On the left are the DPS current values, followed by the Solartron measurement, and column C is the Solartron values converted to amps by multiplying. Then we have the values from the multimeters in the same order as they were in the images. First the rapid test MAS830L, then the 2 Maplin sinometers, the big being Q, no name, and finally in column H the UNI-T. Following these are calculated error percentages against the Solartron. The error columns are in the same order as the multimeters. Finally, the graph. Okay, oops, maybe slightly too. There. This is the errors against the current, which pretty much confirms the first impression. The 2 sinometers, and they claim an accuracy of 1% in the 10 amp DC range, and amazingly they are still almost there, certainly within 1.5%. I found no specs for the big meter, but it's also well in the 1 to 1.5% range. Discard a large excursion here at the very low end. As I explained before, this is not real. The blue curve of the MAS830L is too high, but actually still within the 3% tolerance of the spec for the 10 amp range. I'm not very impressed by the UNI-T though. The spec for the 20 amp range, which I used, is plus minus 2% plus 3 digits, but I'm getting more like 6% under reading. Well, my main goal was to experiment with getting real measurement values from external sources synced with the control and recording of the DPS5005, and this works just fine. During these experiments, I have now verified the actual readout accuracy of my DPS5005, which turns out to be around 0.2% for volts and 0.5% for current, and the automation made taking and recording the 2x100 measurements totally effortless. And with only a little bit more work, I now got a good idea about the DC current accuracy of 5 of my multimeters. For now I'm limited to the DPS measured values and images from webcams and readings from GPIB bus devices, of which I own exactly one, but I plan to add other interfaces and remotely readable meters eventually. Thanks for watching.